Good morning, everyone, and happy Friday. My name is JR from Land Effects, and I work in the Manufacturer Connection Department here. We have a special treat for you. Today, we have Justin McDaniel from Munro. Fortunately, we were able to snag Justin out of his extremely busy schedule to go over the little things that make a difference in your pump station. We all know that for those projects where we need to get water from one location to another, we know the pumps are extremely important. And I'm excited to have Justin show us all today what that looks like to enhance the pump station design. Before we get started, just a few housekeeping items. First of all, the webinar is being recorded, which will be uploaded later on today for you to fall back on. If you have any questions, please use the Q&A button at the bottom there, and we would be happy to pass those along to Justin. As always, the chat box is there and a great place for any comments, banter, or just to chat amongst yourselves. Lastly, if you are viewing this in full screen and want to exit, just hit your escape key and you'll be taken out of full screen. With all that said, I know we got a lot of content today, so I'd like to turn this over to Justin. Justin, take it away.
Appreciate everyone joining us today for this webinar we're putting on. The little things that matter make a big difference in your pump station design. We're going to talk about some of the things that we find create big impacts when making decisions on how we design pump stations. So if they're not known or disclosed or understood, it can help us to determine what's necessary and what we're going to put together as a pump station. We'll share some stories. We'll invite you to share some stories with us that you might see in some of the projects you've worked on. All of the topics listed here have an impact on the system design. So we're going to talk about things that we feel are something that needs to be looked at as we put the station design together itself. So there are many things to consider when designing an irrigation pump station. We'll explore some pump styles, typical styles that are used for irrigation applications. We're going to talk about minimum flows and how the performance of the pump is affected. We're going to talk about using single or multiple variable frequency drives. These VFDs can control a single pump, or they can be coupled to control multiple pumps. We're going to talk about enclosures and the type of enclosures that can be added to an irrigation pumping station. We're going to talk about vertical turbine seals and what is the best type of seal for vertical turbines. And we're going to talk about pressure tanks and how to apply them and the best use for pressure tanks themselves. So to start off, we're going to focus on horizontal and vertical multi-stage centrifugal pumps. These are two of the most utilized pumps for irrigation applications. Some of the pros and cons to these. Horizontal pumps have good MPSHR characteristics, meaning that they have the ability to lift water fairly well. Horizontal centrifugal pumps can handle dirtier type water. They can be used for booster suction lift applications. So if we have an available pressure to us, we can boost the pressure from a minimum to whatever the irrigation system design might require, or we can lift the water out of a pond. This style of pump is really fairly available from a manufacturer, so it can shorten lead times when it comes to building pumping stations. And it can be lower cost compared to the alternative we show here, the vertical multi-stage pump. Cons for the horizontal centrifugal, sometimes they have a lower efficiency in some cases, and they typically run at lower pressures than a vertical multi-stage pump does. Some of the pros to a vertical multi-stage pump, they offer higher efficiencies, so we can possibly get away with a little less horsepower when selecting this style of pump. They work very well for booster applications, so we can boost available pressure to a given pressure for an irrigation system. And they offer higher operating pressures also because they're a multi-stage pump with multiple impellers built into the pump itself. Some of the cons, not overall, or not a good fit for suction lift applications. We typically at Munro do not apply vertical multi-stage pumps for suction lift applications. Mostly they're applied in booster type applications. They typically are a little higher cost than the horizontal centrifugal pump. And trying to get a hold of that pump sometimes can be challenging. The parts are not necessarily readily available as they would be compared to a horizontal centrifugal pump. So the horizontal centrifugal design is the most widely applied pump in the irrigation industry. That's the style of pump most applications we see are going to be utilizing. It lifts water and boosts water based on the application. The efficiency is moderate based on the pump selection, and there are different varying ranges of efficiency that we can select when it comes to this style of pump. They're very cost effective and they're easy to maintain. That's one of the benefits to using a horizontal centrifugal style pump. Vertical multi-stage design, highly efficient pump, capable of high pressures and high flows, higher repair and maintenance costs. These could be somewhat challenging to work on and a little bit harder to work on than a horizontal centrifugal. Excellent pump for surface water applications that require high flows and high pressures. So if we can get flooded suction to these, they will work well for boosting pressure. The difference to a vertical multi-stage and a horizontal centrifugal is the number of impellers in the pump. Typically, a horizontal centrifugal has a single impeller. A vertical multi-stage has multiple impellers, and that's what allows for higher pressures or operating pressures from the vertical multi-stage pump. So why this makes a big difference? There are multiple styles of pumps that are available to us to build a pumping station. And all of these different styles can accomplish the same job. But when we look at cost, efficiency, and overall effectiveness of the pumps itself and the selection of the pump, typically we look at these two styles for most of the applications we do. We need to determine the trade-offs that matter most. So what's the bait, are we looking at cost? Do we go with a horizontal centrifugal because the cost is lower? Or do we go with a vertical multi-stage because we're looking at higher efficiencies? And when it comes to higher efficiencies, maybe we can reduce the amount of energy that's necessary for the system to operate. Maybe the efficiency, the longevity, is it easy to service? Horizontal centrifugals are easy to service. Vertical multi-stages are not necessarily easy to service. Overall cost, there is a trade-off in cost there between the two different styles of pumps, where horizontal centrifugals typically cost less money than vertical multi-stage style pumps. Both pumps work well for irrigation applications, and it just really is a discussion with the manufacturer on what style of pump, what's the application, so that we are applying the correct pump to fit the needs of what the irrigation system requires. So that's one topic. Overall materials of construction sometimes can be looked at for vertical multi-stage versus horizontal centrifugal. Typically, you're going to be a stainless steel pump versus a cast iron pump. How quick do we need the pump? Are we looking at a horizontal centrifugal because we can get it faster than we can get a vertical multi-stage? And availability is all part of what we look at when it comes to designing an irrigation pump station. The next topic I want to talk about is minimum flows. Minimum flows can be challenging for pumps and how they operate. And typically when we look at it, one of the questions is, can one pump do both high flows and low flows applications? Are we running drip zones? Do we require much lower flows than we might for turf rotor zones? So looking at that, do we determine we need to only run one pump and we can manage the minimum flows and we can manage the maximum flows? That's something to take into consideration. And that's all about design. A lot of manufacturers have standard products that are single pump, variable frequency drive pump stations. And then they can get into where we do multiple pumps on the package. So maybe a simplex, a triplex, or a duplex type pump station. All of those can be considered and allows us to look at multiple or low minimum flows. The next screen, we need to understand the performance of the pump and what minimum flows affect the pump and how the pump is going to operate with minimum flows. So if we look at this curve, this kind of talks about operating the pump in the most efficient point of the curve and what happens when we run low flows and what happens when we run high flows. So under low flows, we'd be operating on the left side of the pump curve. As we see, if we're running too low of flows, we might have a temperature rise that happens here. As we start to move farther right on the curve in our selection, we might start to see a little bit of cavitation happening at really low flows. The next stage would be, minimum flows, acceptable bearing life and seal life. So this is basically where we really want to start our minimum flows at. and run to the right of the curve. If the system requires that we have maybe a 20 gallon a minute zone and a 300 gallon a minute zone, is it possible to turn the pump down to run the 20 gallons a minute without damage to the pump? This curve is explaining the different points on it and how it's operating. So high temperature rise, noisy operation. We're getting to a point where bearings don't necessarily hold up very well. Low flow limit, so we could start to get into cavitation. Here in the middle of the curve, we're starting to see some suction discharge recirculation. So at the eye of the impeller, everything is starting to move itself around in a manner that's not working well for the pump. Here is the most efficient point where the suction impeller is shockless entry. It's running perfectly. Water is going into the impeller, moving itself perfectly, and we might be at that higher flow. But to try and turn it down to the lower flow becomes a big problem for the pump. So the consideration would be we would move to maybe 2 pumps where we can handle lower flows as opposed to the higher flows. And maybe 2 10 horsepower pumps where we can do the 20 gallons per minute and we can still get to 300 gallons a minute out of both pumps. So the reason for discussing this is that, you know, as designers and manufacturers, we want to try and gather as much information as we can. And one of the questions that we ask is to provide the minimum flows along with the maximum flows so that we can take a look at whether one pump will work for the project or if we need to look at multiple pumps to make the project work. So knowing this information up front is a big deal for us. Minimum flows can have a significant impact on the design of the pump station. So again, gathering this information is a big deal for us. There are benefits to using multiple pumps, but there is issues with there's a potential cost increase versus longevity to reduce maintenance of the pump itself. And applying it at a situation where if we have 2 pumps, we might have a little bit more cost in the overall pump station than what 1 pump would have. But the operation of the system would work much better for lower or higher flows than it would for lower flows. Any questions or thoughts on minimum flows for pumping stations?
Looks like we are all good right now. Thank you.
Okay. So the next topic I want to talk about is single or multiple variable frequency drives. This is a big topic that multiple manufacturers discuss quite often and how they design their irrigation pumping stations. Munro's standard approach is to use a VFD for each motor that's on a pumping station. Other manufacturers sometimes use 1 variable frequency drive for each motor that's on the pump station. And with that becomes trade-offs and efficiencies of the overall operation of the pump station and the effectiveness of the process of the pump station. Typically, when we use 1 variable frequency drive, it is coupled to all 3 motors. We'll take a triplex pump station, for example. It may be connected to all 3 motors. Here's an example of a triplex pump station. So the variable frequency drive would be connected to all 3 motors, and as the system process stages the pumps, it'll call for the first pump to start and use the variable frequency drive to ramp itself up to full speed. Once it reaches full speed, then it will swap from 1 motor to the next motor and allow 1 motor to run full speed while the second motor in line has the ability to adjust speed up or down with the variable frequency drive. And they would stage the next pump. Once it reached full speed, then it would swap it over to the next motor. That next motor would speed up and slow down based on the variable frequency drive. Munro's approach to it is to use variable frequency drives on each motor. With that, we can assure that we have a soft start to each motor. It can speed itself up and slow itself down, and it can start to change the speed to become more efficient in how it operates. Now, drawbacks to this, obviously, is that it can be more costly to add variable frequency drives to each motor. But in the overall scheme of efficiency and process of the pump station, we can start to gain energy savings because we're using multiple variable frequency drives in how we control the pumps. Other ways of starting and stopping pumps with one variable frequency drive is to start one motor across the line. Typically, that's a hard start. It comes up to full speed. And then a variable frequency drive would come on afterwards. And the VFD would speed itself up and slow itself down based on the required pressure in the system so that they have the ability to just use the one variable frequency drive. If for some reason we lose the variable frequency drive on that system, we no longer have the soft start capability or the process control that the variable frequency drive affords us. So with that, we start to lose the efficiency and how the irrigation system operates. We could start to see some overpressuring in the system. We may have to add valves to the irrigation system so that we can throttle the pumps to keep them from either overloading or overpressuring the system because of the loss of the variable frequency drive. Variable frequency drives themselves are typically used on just about every irrigation pump station that's out there much anymore. And the approach to each manufacturer's design is based on the control scheme that each manufacturer puts together, allowing us to become more efficient in how it operates and control pressures and flows much easier with the variable frequency drive. So why it makes a big difference, there are several control scenarios that are possible. Multiple variable frequency drives offer flexibility and added efficiency. You must understand the power availability at the site so that we can make a determination on what size and what voltage we're going to be running for each motor. But it's pretty important that we understand what we have for power there. Control scenarios will affect the cost, upfront costs versus total cost of ownership. So knowing that we have multiple pumps on there, are we going to use one variable frequency drive? What's the cost of using it? Are we going to use multiple variable frequency drive? What's the cost of doing that? There are different costs to it, but we can again make up some efficiencies in how we operate the irrigation system with multiple variable frequency drives. Any questions or thoughts on how we might use multiple variable frequency drives versus single variable frequency drives in an irrigation system?
Looks like we may still be good as of right now. Nothing in the chat. Once again, reminder that if you have any questions, please throw them in the chat and we'll throw them over to Justin. But I think for right now, we're good.
Okay.
Oh, do you want to actually, I'm sorry, there's one that just came up. Any thoughts on cycle stops?
Thoughts on cycle stops. So cycle stops are an older technology that doesn't necessarily compare to the technology that variable frequency drives afford. What I mean by that is that we can control current much easier and pressure much easier with the use of variable frequency drives, where cycle stops are pretty much a pressure relief valve. And they're a throttling valve of some sort that allows head pressure against the pump all the time. And as we exceed a given pressure, it starts to let more water through the system. If we're going to be doing large irrigation systems with huge varying flows, the better way to handle would be with a variable frequency drive. Smaller irrigation systems with smaller flows, a simple valve on it could be beneficial and may make the cost a little less than it would be with a variable frequency drive. I can tell you that the overall current change is going to be much higher than with a variable frequency drive than it would with a cycle stop valve. There's limited current change with a cycle stop valve. So the technology works when it comes to cycle stop valves. Munro's preferred way of operating a pumping station with variable frequency drives, just because we can gain a little bit higher efficiency and better process control with the variable frequency drives themselves. Hopefully that answers the question there.
Yeah, perfect. Thank you. So, a couple more in here in the chat. Do you use any flow control valves to control the PSI and flow?
So a cycle stop valve would be an example of a flow control valve. A simple butterfly valve could be an example of a flow control valve where we're throttling the head pressure against the pump. can be done with a automatic style valve with an actuator on it, where it can modulate itself open and close if necessary. I think the use of the variable frequency drive, though, again, outperforms the use of throttling valves. Um, Cost is definitely going to be a different change there. But the use of variable frequency drives over throttling valves is a much more preferred way of managing flow control itself.
Perfect. What about use of a vertical turbine pump?
Vertical turbine pumps are definitely a selection that is looked at. Um, in this webinar, we were trying to, compare the two biggest styles we see. Vertical turbines is the next style that we typically would build a pumping station with, and that vertical turbine is going to be a very efficient pump. It's going to be a style of pump that would be installed on surface water applications most of the time, where we're lifting water maybe from a pond or a lake or a tank of some sort. Vertical turbine style pumps offer, as I said, higher efficiency, but can offer much higher flow ranges than horizontal centrifugal pumps might be able to. In addition, vertical turbine style pumps can be multi-stage pumps where we can build much higher pressures to accomplish the given requirement for an irrigation system. So if you were to compare a vertical turbine maybe to a horizontal centrifugal, and we've got an application where we're at maybe 110 psi to operate the irrigation system, because of the efficiency of the vertical turbine pump over a horizontal centrifugal pump, we might be less horsepower and we might be quite a bit more efficient than what a horizontal centrifugal pump might afford us. So with that, I mean, vertical turbine pumps are great pumps. They're very expensive pumps. They're hard to maintain. They're not something you can pull out real easy and take to a shop or just work on in the field, where a horizontal centrifugal pump would be something you could work on in the field. Big difference in the styles of pumps themselves. A great pump for irrigation applications, though, for sure.
Perfect. And do VFDs work better with three-phase power?
Variable frequency drives have the ability to work with both three-phase and single-phase power. It's all about how the variable frequency drive is sized to manage the power source itself. So when it comes to efficiency, three-phase is the most efficient way to operate on a variable frequency drive or operate an overall irrigation system. To utilize it on single phase power, typically we are oversizing the variable frequency drive by sometimes as much as 2.5 to 3 times larger than the motor. Per National Electrical Code, we have to wire the input amp rating of the variable frequency drive and not the motor. So we lose the efficiency there. If we're sizing a variable frequency drive that's 2.5 to 3 times larger than the motor, we need a lot more power at single phase than we would with three-phase power. So ideally, during any system design, researching whether you can get the three-phase power to the site is the best scenario. If it's available, then yes, either 208 or 480 volt three-phase is the ideal way to run it. There are
Awesome.
other issues with variable frequency drives that come into play when it comes to making phase conversion, but inefficiency is definitely there with the use of single phase power.
Awesome. Thank you so much for answering those. That is all that is in chat right now. We'll go ahead and keep watching and send them over your way when they come up.
Okay. So next topic I wanted to talk about would be enclosure options that manufacturers can offer for irrigation pumping stations. Um, there are all kinds of different styles of enclosures that can be built. We can look at site-built enclosures. We can look at custom-built enclosures, maybe aluminum enclosures or steel enclosures, things of that sort can be added to an overall enclosure system. Designed to house all the equipment. We can add insulation to them. We can add heaters to them. We can add lighting to them, GFCI plugins to them. All of the things that might be necessary while you're on site to possibly work on the pump station, or take in consideration the environment that the pump station is going to be in. Colors can be all kinds of different colors. Munro's typical standard is to use an aluminum style enclosure and powder coat the aluminum style enclosure. With adding the insulation and the heater to it, might work well in environments that is cold in the spring and cold in the fall. A lot of times in the past, I've seen that people get a little overzealous and they want to put their irrigation water out on an irrigation system early spring. They'll go get it primed, they'll get it turned on, they'll irrigate for a couple of days, and then a couple of days later, it'll come in and freeze again on them. Adding insulation and heaters to it will help protect the components that are on the pump station, whether it be pressure transducers, pressure gauges, or even if it's hard enough to freeze the overall pump station. That ability is there to work with it in environments. Other reasons you might use insulation might be for sound dampening. There are applications I've seen in the past where the pump is fairly loud or is located somewhat close to a residence, and they want to be able to quiet the pump down so that the residents can't hear the operation of the pump system. So some of these things can be added to the pump or the enclosure in order to take into consideration the environment that the pump station is going to be in. Here are some examples of different types of enclosures we've seen in the past. This is a concrete pump house here. The pump house was existing. We ended up putting some submersible pumps next to a pond to pump out of the pond, and we utilized the existing pump house they had built there. Another example is just a lean-to built over the top of the pumping station. This would be environments where it's continuously warm all the time, and the pump station is running pretty much year round. So there's a couple of options that could be looked at there for the style of enclosure that would be used. So one of the biggest takeaways when you're talking to a pump station manufacturer is to convey all the environmental information that's necessary, right? Are we going to be dealing with cold weather? Are we dealing with warm weather? Do we want to worry about sound dampening so that we're not upsetting the neighborhood because the pump's a little louder than they expected it to be when it was running? Discuss any special appearance needs, right? What colors are we looking for? Are we looking for a specific color on this pump station? Will the standard factory color work for the application? There are many different styles of colors that can be added to any of these pumping stations. We talked about temperature control, sound dampening, attenuation can be addressed, but it must be known. So these are things that you want to think about when you're designing an irrigation system or requesting an irrigation system. What are some of the other things that I need to add to it for sure? Any questions or thoughts on enclosures? Okay.
Excellent. Yep, good to go.
So one of the things I want to talk about also, there was a question about vertical turbine pumps here, and specifically I want to address the type of seals that can be utilized in vertical turbines and what's the best seal to use for the application itself. There are multiple different ways to seal a turbine pump. I'm going to talk about two that are typically used in irrigation applications. A mechanical seal and packing seal. Here, we'll talk about a little bit about the different styles and what they do. So a stuffing box is what we call the packing style seal. It has a soft packing ring or a rope that's compressed against the shaft. It needs frequent attention. That's a big deal about it, is that it needs to be maintained. It can burn up if not enough liquid is running past the packing itself. So typically we expect this style of seal to drip or send water past the packing rope that's in the stuffing box in order to keep it cool. It always leaks as part of the design. That's a big deal. It needs to be dripping water so that it can keep the shaft cool and keep everything sealed up properly. The other style is a mechanical seal, and it consists of a rotating element, a stationary element. This provides the best sealing ability for this style of pump so that we don't have water dripping across the packing and basically creating what we see here, a very large mess on a pumping station. This pumping station uses mechanical or packing seals, and water is constantly leaking on the pump station. As you can see how much water is sitting on top of the pump station. It's gotten to the discharge heads on the pumps. It's gotten up into the bearings of the motors because we have so much water moving around that it can be detrimental over years if it's not maintained properly. So an example we use this for is we ended up changing this pump station from this style of pump station to a newer style of pump station. And with that, the new style of pump station included mechanical seals. As you can see the difference in how clean the pump station looks after being in operation for several months. We have no water dripping across the pump station. There's not a big mess. We're not worried about our skids rusting out or any of the other components that are on the pump station rusting themselves out. Another example of what it looks like. Um, some considerations for the styles of seal that we use. One of them might be the type of water that we're going to be using. Packing seals are very good at handling water that is highly turbid and has a lot of material in it that could be damaging to a mechanical seal. So maybe we might be pulling water directly out of a river. If we're pulling water directly out of the river and it didn't have an opportunity to settle itself out, we could be pulling a lot of material up into the pump that could cause damage to a mechanical seal. So we might want to select a packing style seal in an application like that. Other applications might be where we're pumping water from a pond that has the opportunity to settle itself out. And when it settles itself out, we're not pulling near as much material into the pump that could cause damage to the seal. Thus, in turn, making the pump station look cleaner, last longer, and just be an overall better solution for the type of seal that we might use. So a couple of considerations is the style of water, the type of water we're going to be pumping, and overall cost can be a big difference too. Packing style seals typically are going to be a little less money than a mechanical seal, but there is maintenance involved with the packing style seal where mechanical seals require very little maintenance. Short of, if there is a seal failure, then it's all about changing the seal out. Where packing style seals, they have to be maintained, they have to be changed constantly. So you're always pulling the old packing out, putting new packing back in order to maintain the operation of the pump in its proper state. So some takeaways here. It's very important to include the information about the water quality and content. We really need to know. I mean, are we pulling water directly from a raw water source that's very, very dirty, or are we pulling water from a raw water source that's fairly clean? Either packing or mechanical seals can be the right seal. It just depends on the application. Retrofits may be able to take advantage of changing to a mechanical seal. So turbine style pumps can be changed from packing to mechanical style seal. Mechanical seals do bring a potential cost increase versus longevity to reduce maintenance, total cost of ownership of the pumping station, right? If the operators are not out there working on the packing all the time and checking it, depending on operation, maybe weekly, maybe monthly, that can cost the overall end user some money in how the pump station is maintained, in addition to the overall life of the pump station and how much water is actually caused, possibly rusting to the pump station and failure of the skid system itself. Okay, any questions on vertical turbine seals and why we might select one over the other?
I don't see any right now, but a quick question for me is from packing to mechanical, it sounds like one is more of an upfront cost and one is a more longevity cost. Do you see that those typically, weigh each other out, that they come out to be a wash?
Yeah, typically they're going to come out to be a wash based on the required maintenance that's necessary for the packing style seal. Upfront cost on the vertical or on the mechanical seal can be fairly significant depending on the style type of seal that is selected. And there are multiple styles of mechanical seals. A very simple one is just the stationary or and the rotating element. They make two-piece type seals that are easier to install. Obviously, a little higher cost with the two-piece seal. But there are multiple types of seals, and as far as cost goes, yep, it's upfront cost versus longevity cost or total operating costs.
Awesome. Thanks for answering that. I appreciate it. Even the three-phase one?
So The three-phase typically deals with power and not necessarily the mechanical components of a pump. And the packing or mechanical seal would be considered a mechanical component of a pump as opposed to what a motor might be.
Okay. So there is one question that just came in and says, how about the seals for a horizontal centrifugal pump? Do those need maintenance as well?
So horizontal centrifugal pumps can be ordered and manufactured to utilize both mechanical and packing style seals. Um, I would say the majority of irrigation application pumps are going to include mechanical style seals. And there is very little maintenance required to a mechanical style seal used in that application for horizontal centrifugal pumps, short of when there is a failure at a mechanical seal. Failures could be caused because of the water that we're pumping through it. Most of what I've seen when it comes to a failure of mechanical seal is because the pump is run dry. When it runs dry, it doesn't have the proper cooling ability to cool itself. So the seal itself starts to fail, it starts to leak, and then it becomes a problem. So catching that early enough to make sure that you're working on it or replacing the seal as soon as possible so that we don't have damage to either the mechanical components on the pump station or possibly the motor. Um, but very little maintenance required for a mechanical style seal in a horizontal centrifugal pump.
Awesome. Thank you so much. That
Okay, the
is
next topic is pressure tanks. And I get asked a lot, does your pumping stations include pressure tanks? Um, Munro does not typically use pressure tanks on our pumping stations. Why you would use a short or a pressure tank on a pumping station would be to control short cycling. Short cycling is the starting and stopping of the pump very quickly to maintain its operational pressure in the irrigation system. Another reason might be for expansion, heat in certain parts of the company. Take Arizona, for example. Sometimes the piping is exposed to the sunlight. And if the system is not operating and it's just sitting there idle all day long with the sun beating down on the pipe, eventually it starts to heat the water up. When it heats the water up, it starts to expand. Expansion tanks might be utilized in that application so that it has a place for the expansion of the water to go to. If we don't allow for that expansion sometimes, then we could cause damage to some of the accessories that are on the pump station, maybe like pressure gauges or pressure transducers, things of that sort. So in certain applications, we might look at a expansion heat expansion tank on a pump station. Other reasons might be for water hammer. Water hammer can be a big deal, and the use of pressure tanks for water hammer can be used to absorb some of the water hammer that might happen in the irrigation system. The next screen here kind of talks about the application and what size pressure tanks might be utilized if it were requested to be used or put on a pumping station. If we look at the chart here, it has a pressure range here at the top of a 40 to 60 range. So if the irrigation system was designed to run at 60 psi, and the pressure was allowed to drop to 40 psi before it turned on, this tells us how much water is available based on the size of the tank. So if we look at a 119-gallon pressure tank, at a 40 to 60 pressure setting, we have availability of 32.1 gallons of water before we reach 40 psi. So we're going to draw 32.1 gallons of water out of the tank at 40 psi. Then it's going to trigger the pump to turn on and maintain the pressure back to 60 psi. By doing this, this can help control the short cycling of an irrigation system. Utilizing a single pump gives us 32 gallons of water. If we have an irrigation system that is designed at 300 gallons per minute, and we're only going to have 32 gallons of water available to us, we may not have enough storage of water to control the short cycling of the water of the pump station itself. So we might want to consider adding a couple of these pressure tanks to get us to a point where we don't short cycle as much as we would with a single pressure tank. In short, when utilizing pressure tanks and applying them properly, it may take multiple pressure tanks on a pump station in order to control the short cycling to a manner that is acceptable. Alternatively, we can use variable frequency drives. With those variable frequency drives, we can do some controls that allow us to not use variable frequency drive or not use pressure tanks, sorry. So by not using the pressure tank and applying a variable frequency drive, we can control the short cycling much easier than we might if we didn't have a variable frequency drive and we were just applying a pressure tank to it. Pressure tanks can be useful, but in large irrigation systems, most of the time, we have enough storage of air in the irrigation system that we can control the short cycling very easily with just the variable frequency drive. Again, typical uses for pressure tanks are going to be short cycling. Usually there's enough air in the irrigation system to accommodate what a pressure tank would accomplish. We might consider it to use for heat expansion. It doesn't need to be a very large tank to control the heat expansion. And for larger tanks to control water hammer, we may need to have a lot of tanks or a very large tank on there to be able to control the water hammer might happen in an irrigation system. Really, in short, unnecessary components can cause issues. I think in the technology that we have today available to us, pressure tanks are not needed and can sometimes be an issue when applying them on pump stations. We just want to be sure we identify the purpose of the tank or not use the tank at all. And if we're using VFDs, the need for a tank might not be there. We might not need to use the pressure tank itself. Any questions or thoughts on pressure tanks? Okay.
There is one that actually just came in right there at the last minute. Other than a pressure transducer, are there any other necessary devices to include in the pump station, i.e. a flow switch or flow sensor, temperature sensor, or switch?
So yes, there are some other components that would be added to a system. Temperature sensor for sure on a pump. Temperature sensor would control shutdowns based on the need for the water getting too hot. Maybe we have a stuck zone valve that didn't open and the pump is just continually running. With that, the temperature sensor itself would be able to detect that the water is not being pumped and would shut the pump down. This could save a mechanical seal in any style of pump that's out there because the water didn't get too hot and cause the seal to fail. Flow switches, that all depends on the control scheme that the manufacturer is using to operate an irrigation system or a irrigation pump station. Some manufacturers do utilize flow switches to either start and stop a pump as opposed to pressure. They might use it to what we would call lock the pump on so that if we're above a given flow, the pump continues to run and doesn't shut down until the flow becomes low enough that it can shut itself down. Other sensors, there's not too many other sensors that you typically would see on an irrigation pump station for the overall process of the pump station itself, meaning we wouldn't see too many float switches or things like that. It would just be, maybe a flow switch, pressure transducer, and some pressure gauges that we're able to look at. Hopefully that answered the question.
Yeah, great. Thank you so much for answering that. That is all the questions in the chat at the moment.
Okay. So as a wrap up here, there are many things to consider when designing an irrigation pump station. And we discussed the pump styles. Multiple styles can accomplish the same task, but there are trade-offs. There's cost differences. There's efficiency differences. All kinds of different things can come into play in making a decision on the style of pump to use. Minimum flows can have a significant impact on the design. If our flows are too low for a pump that's very large, then we want to split it up into a couple of pumps so that we can manage the minimum flows or the low flows that are going to be happening with the irrigation system so that we don't cause damage to the pump while it's operating. Single or multiple variable frequency drives, different control scenarios affect the total cost of ownership. So if we're using one VFD versus multiple VFDs, there could be a cost difference there. But there are trade-offs to that also, and that is how the operation of the system is utilized as far as process control. And can we be more efficient with one VFD or multiple variable frequency drive? Well, the answer is multiple variable frequency drives. We can be very, very efficient in how the system operates itself. Enclosures, consider the options and features, right? Are we worried about environmental control? Are we worried about the color of the enclosure? Are we worried about the style of the enclosure? What's available? Does it make sense to build something on site? Does it make sense to have the irrigation pump station manufacturer manufacture the enclosure itself? Lots of things to consider there, and these are things that, as designers yourselves, should be considering in order to convey the correct information to the irrigation pump station manufacturer. Vertical turbine pump steels. We want to provide the information on water quality and recognize that there is a difference there. There's a difference in cost. There's a difference in overall maintenance, things of that sort. So consider that while conveying information to the pump station manufacturer. And then pressure tanks, we really want to understand the purpose. They're not always necessary. Technology nowadays can let us get away without utilizing pressure tanks on pumping stations as we might have done maybe 30, 40 years ago. So those are pretty important things to all consider while conveying information to the pump station manufacturer. And looks like I'm finished with the overall discussion here today. Is there any questions?
That was perfect timing. There was a question that came in right as that screen went dark there. So Chris wants to know, is there a percentage of your maximum flow that is recommended for your minimum flow to avoid larger cost impacts?
Yes, there is. Uh, so typically we want to look at about maybe 15 to 20% of the minimum flow or maximum flow before we start looking at multiple pumps in that range somewhere, so that we do have a pump selected that won't allow us to go to too low a flow and cause damage to it itself. So 15 to 20% is where I typically look at it before making a decision to move to multiple pumps on an irrigation pump station.
And what about thoughts on an irrigation master valve with pump station?
So master valves are definitely utilized in a lot of different applications. We do put them on pumping stations. And one of the biggest things we can consider is whether it's a boost application or whether it's a suction lift application. If it's a booster application, then the master valve might be necessary downstream of the pump station because we've always got positive pressure feeding the pump station. If it's a suction lift pump station, the consideration of a master valve might be not considered due to the fact that the pump station could be treated as the master valve. So we could use the master valve from the irrigation controller to start and stop the water source itself. Where in a booster application, we've always got water. We need to be able to shut the water off so that we don't have any catastrophic failures out in the irrigation system and cause flooding.
Perfect. And can you have two different pressure settings on the VFD, low PSI to run drip zones and then high PSI to run rotors, i.e., set points on the VFD?
That is definitely possible for sure. Most variable frequency drives, as well as control schemes, have the ability to recognize different zones that may be operating, and that would be from the irrigation controller itself telling the pump station, I'm running drip zones or I'm running large turf zones, and we need to change the set point of the variable frequency drive. So yes, that is completely possible to do.
Awesome. And then do you recommend one duty pump with a jockey pump or two duty pumps that share duty alternative or alternately, so 50-50 each? Someone was saying that we tend to do the latter so that one can be serviced without losing water delivery.
I think that depends on the application. We build them with one duty pump and one jockey pump. We might build them with two duty pumps. It depends on the flow range that we're going to be looking at to get that accomplished. That's really, specifically to, how the irrigation system is designed as to how we might approach getting that accomplished. Two duty pumps, one consideration could be that it does the maximum flow for the overall irrigation system with one pump, or it does the overall maximum flow with two pumps. And then if it does the overall maximum flow with two pumps, can we reach the minimum flows that are necessary for the operation of the system? If we can't get down to the minimum operating flows with two pumps, then we might consider adding two pumps and a jockey pump. There's a lot of different scenarios that can come into play there in how the pumps are staged or assembled on the pump station for sure.
Can we have a pump station which uses a bypass for the drip zones or basically using the available lower intake pressure and only boost for spray and rotors?
Yes, that's very easily done too, and that's management from the irrigation controller itself. The irrigation controller can say, all right, for zones 10, 11, and 12, I got turf zones, I want to run the pump. For zones 13, 14, and 15, I do not need the pump, so don't start the pump. That's one way to manage that.
Perfect. So Munro Pumps, we have Justin McDaniel with us today. Munro is in the land effects system where you can specify Munro pumps for your designs. Justin, talk to us more about what Munro pumps, like what's your specialty at Munro? What would you say your pumps are best used for?
So Munro focuses on irrigation applications. That's what our products are designed around, and what we focus on 100% of the time is irrigation. There are many, many um, industries out there that utilize pumps for all kinds of applications, but for Munro, we specialize on irrigation, and that's what we really focus on. And we have a lot of background and understanding and knowledge about irrigation itself. From coupling it to, different irrigation manufacturer controllers to overall system design and how irrigation pump stations work with irrigation systems themselves.
Fantastic. Well, that's all the questions that were in the chat. Justin, thank you so much for a wonderful presentation. There was a lot of information there, a lot of answers being given to questions that were had in the chat. We thank you all for being with us today, and I hope you all have a great weekend.
Thank you, everyone.